Hi, in this video we are going to find the formula of the electric field due to this charged circular disk. And we have this circular disk, you see it's drawn here. This circular disk is uniformly charged, and due to this circular disk we want to find the electric field. For simplicity, I am going to fix the axis of this disk at z-axis to be aligned with z-axis. So z-axis is the axis of this disk. I will render the origin to be the center of this disk. In order to solve this problem, the first conceivable way is Gauss's law, which is this is the formula of Gauss's law, but it's not the best choice. By applying this equation, it's mandatory to determine the Gaussian surface, and it's hard to determine the Gaussian surface in this case. So this Gauss's law is not the best choice, as we aforementioned. We are going to find another way in order to solve it. We are going to exploit the concept of the electric potential. We know that the electric potential is measured by this equation. This is the electric potential due to some charge in the free space. And from the electric potential, we can apply the gradient operator to find the electric field. Okay, now in order to use the electric potential equation, we want to find the total charge due to this circular disk, which is represented by Q. This form of this equation is ideal when we are dealing with discrete charges, but in this case the charges are distributed continuously on the surface of this disk. So it's better to use another form of equation. I am going to take a small piece from the surface of this disk. This piece you see here is the small differential surface from the whole surface of this disk, and I'm going to call it by ds. Okay, the charge due to this small differential area is equal to the charge density times the area of this small surface, and let us substitute this inside this equation. This is the potential due to this small piece of charge. Okay, in order to find the potential due to the whole charge, we are going to take the integration to calculate the total charge. Okay, A denotes to the area. Okay, and R is representing the distance between this small differential area and the point where we want to measure the electric field at. Let's determine this point to be here. This point, according to Cartesian coordinate system, is going to have the coordinates of 0, 0, and let's say z. Okay, z is the distance between the origin and the point. Okay, then this line is z. And r, we said, is the distance between this differential area and the point. We want to determine this differential area by using either Cartesian or spherical or cylindrical coordinate system. In this problem, the best choice is going to be the cylindrical coordinate systems. Try to compare it with this cylinder. In this cylinder, we have 3 axes: z, which is the height of this axis, and r, which is the radius of the base of this cylinder, and we have the azimuthal angle phi. In this case, we can easily determine these 3 axes. Z is already determined, and r is the radius of this circle, of this disk, and phi is the azimuthal angle, is this angle. Okay, now we can write r in terms of cylindrical coordinate systems by using the Pythagorean theorem, as this angle here is 90 degrees angle. Okay, the angle between r and z. And regarding to the surface, I'm going to take a top view from this disk. I'm going to draw the top view over here. As you see, this is a top view from this disk. In order to calculate ds, we want to find the product between these two lines, this line and this line. Okay, we said that this line is r. Okay, this line is the radius, and this line, this is small differential line aligned with it, I mean this line, is the differential radius, as it's aligned with the radius of this circle. And this line, let's say that this line is equal to L. Okay, now this and this angle is the differential azimuthal angle. It's okay, this angle is d phi. This angle here is d phi. Okay, now this angle d phi equal to the line seen by this angle divided by the radius of this circle. This means that L is equal to R times d phi. Now, as we said, ds is equal to the product between these two lines. Then ds is equal to r dr times d phi. Now let's substitute the right hand sides of these two equations for the equal terms inside this equation. And before substituting, I'm going to say that rho s over 4 pi epsilon, all of them are constants, so we can take them out of the integration, and accordingly we will have. And as we see, this integration is converted into double integrations, one for r and one for theta. And as we see, r is ranging between 0 and b, which is the radius of this circular disk. I forgot. Let's say that the radius of this circular disk to be b. Okay, b is the radius of this circular disk. And the azimuthal angle phi, it's ranging between 0 and 2 pi. Firstly, to integrate with respect to r, I'm going to use the substitution. I'm going to assume a new variable, let's say delta. Delta this is equal to z squared plus r squared. Now let's take the first order differentiation for both sides. Regarding to the range, the new range, I'm going to substitute 0 and b in this equation. Now let's apply the new variations upon this integration. And if you are asking about d phi, I'm going to integrate directly. The integration of d phi is equal to phi, and the integration of 1 over 2 delta to the power of half is equal to delta to the power of half. Now let's substitute this for this integration in this equation. And regarding to this, the answer is going to be 2 pi. And you can apply this by yourself, the rest of this. And I'm going to write the final answer directly. And this is the final answer. This is the electric potential due to a circular disk. And in order to find the electric field, we are going to apply the gradient operation. We know that the electric field is the negative gradient of the electric potential. The electric potential is the derivative with respect to the three spatial coordinate systems. We said that in this problem we are going to use the cylindrical coordinate systems, which is consistent of r, theta, phi, and z. You see in this formula we have only r, we don't have phi nor z. Accordingly, we are going to only differentiate with respect to z. As you see, I wrote this on a new paper. Now let's start differentiation. We all know that the differentiation of this is equal to z. We are going firstly to take the derivative for z squared, which is 2z. Then we are going to take the differentiation for the whole term, z squared plus b squared to the power of half, and the final answer is going to be this. And regarding to this, this can be found by firstly taking the differentiation for z, which is 1, times what is inside the absolute parameter, which is z, divided by the modulus of z. Now we are going to split this into two parts. One of them when z is greater than 0, or namely the electric field above the circular disk when z is greater than 0, and when z less than 0 when the point is under that disk. Now let's split this into two sides, as we said. Now, as we see, this is the equation for the electric field. Just sorry for this, just I forgot to add the to the unit vector there. I will add it. Okay, it's az. And this equation can be simplified by using the approximation. For the most of times, the point that we want to measure the electric field at is far away from the disk. Okay, or by other words, for the most of time, z is significantly greater than b. Okay, whereupon this can be simplified to by using the binomial expansion. We are going to simplify this. If you don't know what is the binomial expansion, I'm going to remind you by writing the equation of the binomial expansion down there. Now let's apply it. Okay, in this equation, the second term and the higher order terms are significantly small when we compare it to the first term. So we are going to cancel out the higher order terms. Okay, and this will be approximately, this term is going to be approximately equal to 1 is equal to this term. So let's substitute this inside this equation, and the answer is going to be, just let me write it on another paper. And now by substituting this term by this term, we reach to these two equations. Okay, now we can add pi to the numerator and the denominator. Okay, and as you notice, in this term, b squared times pi times b squared is equal to the area of this disk, and the area of this disk times the charge density is equal to the total charge on this disk. Okay, and the same thing for the for this term. So the final answer is going to be, and this upper formula is for z is greater than 0, and the lower one when z is less than 0. And as I said, q is the total charge on this q is the total charge on this disk. And this is the end of our lesson for today. See you.